Here's the video version of the equilibrium calculations lecture. In any equilibrium calculation, the first thing we want to do when solving our problem is to read carefully through what we're given and make sure we're clear about what the problem is asking us to find. Then we go about finding that unknown by using an equilibrium table. The first step in writing an equilibrium table is to write the balanced chemical reaction, often given in the problem. Then underneath that balanced reaction, we're going to make a table where we put in the initial concentrations, the changes in those concentrations as we proceed towards equilibrium, and finally the equilibrium concentrations. Our equilibrium concentrations are often expressed in terms of X, and so in order to find those concentrations, we want to substitute our equilibrium concentrations into the equilibrium constant expression and solve for X. So once we solve for X, we can then go and calculate the equilibrium concentrations using the expressions for each concentration as given in the table. And lastly, and this is something you should always remember to do, think about your answer and make sure that the answer that you get is the right answer numerically by substituting it into the equilibrium equation to find out if you get the correct equilibrium constant. Let's do a couple of examples of equilibrium calculations. In the first, we're going to find the equilibrium constant Kc from initial and final concentrations. We're looking at the reaction H2 plus I2 gas gives 2 moles of HI. And we're given the initial concentrations of H2 and of I2 at a particular temperature. And we're also given the final concentration of HI, which is 1.87 times 10 to the minus third molar. Okay, we're asked then to find the equilibrium constant Kc. And so the first thing I'm going to do is write down the equilibrium constant expression, which is HI squared divided by the concentration of H2 times I2. Okay, and these are going to be the final concentrations at equilibrium. Notice that we're already given the final concentration of I2. So what we really need to do is find the final concentrations of H2 and I2 to solve the problem. Here is where I use the equilibrium table. What I want to do is look at the stoichiometry of my reaction. What I see is that for every 2 moles of HI, I use 1 mole each of H2 and I2. So if I make 1.87 times 10 to the minus third molar HI, I'll have to deplete my H2 and I2 by half that amount. In other words, the amount of the reactants I use is going to be 1/2 the amount of HI that I make. That's a 3, okay. And that's the same in this box. When I calculate what 1/2 0.187 is, I get 9.35 times 10 to the minus fourth molar. So I substitute that value in each of these boxes for H2 and I2. And at equilibrium, I'm going to have to take my initial value, which is 1 times 10 to the minus third, and then subtract the amount of H2 that was depleted during the course of the reaction. And in the case of I2, since I'm starting with more, I'm going to take the initial concentration, 2 times 10 to the minus third molar, and subtract the amount used, 9.35 times 10 to the minus fourth molar. Doing the math, I find the final concentrations of H2 and I2 at equilibrium. So now, finding the equilibrium constant is simply a matter of plugging in these values. For H2, the 6.5 times 10 to the minus fifth molar. For the I2, the 1.065 times 10 to the minus 3 molar. And recall we were given this value here for HI, and doing the math we get the equilibrium constant is equal to 51. Another kind of equilibrium calculation problem that we'll encounter is to find the equilibrium concentrations given the value for Kc. So here's an example of that type of problem. Here we have a situation where the same reaction, where we're going to react H2 with I2 to give HI, but instead of given the concentrations here, we're told that in a 5-liter flask we have 2 moles each of H2 and I2, and we have no HI at this point. And we're given the equilibrium constant at a different temperature, which in this case is 57. So the first thing we have to do, because we're not given the initial concentrations, is to express those concentrations by taking the number of moles of each of the reactant divided by the volume of the container. So we can see that our initial concentrations of H2 and I2 are 0.4 molar. Now we make our equilibrium table. We start by writing the balanced equation, and underneath that balanced equation we fill in what we know about our reactants and products. In this problem, all we're given is our initial concentrations of H2 and I2, which are the reactants. Since there are no products initially in this problem, we know that the reaction is going to proceed from left to right to give us products. Okay, so now we're going to use the stoichiometry of the reaction. I know I'm going to lose some amount of my reactant. And I'm going to, since I don't know in this problem how much I'm going to lose, I'm going to, for each amount of reactant, call that X moles, or X molar will be lost. All right, so now I'm looking at the stoichiometry, and I know that for every mole of H2 and every mole of I2, I'm going to gain 2 moles of the product HI. So I'm going to gain that, expressed by this plus sign, and I'm going to put in 2x to convey the idea that for every 1 mole of reactant I get 2 moles of product. Okay, at equilibrium then, if I add these two columns, I will get an expression for the concentration of that species. So 0.4 minus x for H2 and I2, and plus 2x for HI. And here is our completed equilibrium table that we're going to be using to make an equation that will give us the value for x. Rewriting the equilibrium constant again, and recalling that this value, Kc, is equal to 57, I can begin my process of substituting in the concentrations from the table. So for HI, remember that concentration was 2x, and I really should have had a parenthesis around that HI concentration, because from our equilibrium constant expression we know that we're going to have to square that concentration. And since both I2 and H2 are equal to 0.4 minus x, I can express that in my equation as 0.4 minus x squared. All right, so noticing that I have a square in my numerator and the denominator, I can make a simpler expression by just taking the square root of both sides. And when I take the square root of 57, I get a number 7.5. Now my problem boils down to just doing the math. I'm going to put in my 7.5 here. Okay, so I need to rearrange this equation in order to find an expression that will allow me to solve for x. So this is just algebra. I'm going to multiply each side of my equation by 0.4 minus x. And when I do that, the 0.4 minus x in the denominator on this side of the equation will cancel. So I have 7.5 times 0.4 minus x is equal to 2x. Now I'm going to expand this. 7.5 times 0.4 minus 7.5x is equal to 2x. Seven 7.5 times 0.4 is equal to 3. And I can now write 3 minus 7.5x equals 2x. Now I'm going to add 7.5x to both sides of my equation, which will give me 3 is equal to 2x plus 7.5x is equal to 9.5x. And x then is going to be equal to 3 divided by 9.5. Which is equal to 0.316. Substituting 0.316 back into my original expressions for the equilibrium constants, for the equilibrium concentrations of H2 and I2, I get that they are both equal to 0.084 molar at equilibrium, and likewise substituting that x value in for the equilibrium constant of Hi gives me 0.632 molar. Let's try another example that's very similar to the previous problem. This time we have a reaction where 2 moles of NO gas react to give 1 mole each of N2 and O2. Again, we're starting off with only reactant so that we know that in this process the reaction towards equilibrium is going to go from left to right. All right, so we're going to be losing our reactant as the reaction proceeds, and we're going to be gaining products. So I'm going to illustrate that by putting the minus and plus signs in the change row. All right, so now we apply stoichiometry. I know that for every 2 moles of reactant, I get 1 mole, which is half of 2. So I can say that for every x moles or molar of NO2, I'm going to produce 1/2 as much of each of the product. And I can write at equilibrium by taking the initial and adding it to the change. In this case, the change is negative, so I'm actually subtracting. I can write expressions for each of these equilibrium concentrations. In the previous slide, I called the change x, minus x rather, and each of the changes in the products plus x over 2, or 1/2 the value of the x moles of NO lost. But equivalently, I can express this same stoichiometry as losing minus 2x moles of the reactant and gaining x and x of each of the products. This gives me different equilibrium expressions. X won't be exactly the same, but so long as I correctly relate all of the quantities using the stoichiometry, the two ways are equivalent. So now I'm ready to substitute the values into my equilibrium expression, and I get, in this case, x squared, because each of my amounts of product have a concentration of x, and I'm going to divide this by 0.175 minus 2x. And because that quantity is squared in the denominator, I would square that concentration value. And notice again that I have a squared term in both the numerator and the denominator. So I can simplify this expression by taking the square root of the equilibrium constant, which will then be equal to x divided by 0.175 minus 2x. And solving as before, I get an answer that the equilibrium concentrations of NO is equal to 0.0018 molar, and the equilibrium concentrations of N2 and O2 are both equal to 0.0866. And by the way, I notice there's an error here. This should have been O2. Okay. In each of the previous examples, we started only with reactants, and we were given our initial concentrations. So in those cases, we knew that the reaction was going to proceed in the direction left to right towards products. But here we have a different example where we have some amount of reactant. In this case, A is equal to 0.18 molar, but we also have some measurable quantity of product at the initial condition. So in this case, it's not completely clear which way the reaction is going to proceed. Is it going to proceed in the direction towards products, or is it going to proceed in the reverse direction, reverting back to reactants? So how are we going to decide? Well, here we need to calculate the reaction quotient Q. This is the ratio of products over reactants at our initial condition, which is not at equilibrium. So this is not at equilibrium. Okay, so I'm just going to substitute in the values that are given for my concentrations. And I get a number, which is, oops, that's going to be squared. And I'm going to get a number, it's equal to 0.31. And we notice that this is larger than our value for Kc. That means that our product concentrations are more than at equilibrium. And when this is the case, to reestablish the equilibrium, we're going to have to, oops, the pen is kind of messing up there. We're going to have to do the reverse reaction, where products are going to revert back to the reactants. So now, since my reaction is going in the reverse direction from products to reactants, I'm going to write a negative x to represent the loss of my products, and a positive 2x for gain of reactants. Now, I notice here I made another mistake. editing these slides a little too quickly. So for this more general reaction, really what I wanted to have in my numerator was product, concentration of product B and C, and in the denominator I would have, instead of NO, the concentration of A squared. Alright, so now I want to substitute in my concentrations of A, B, and C into this equilibrium expression. And I'm going to write 0.2 minus x times 0.05 minus x for the concentrations of B and C, divided by the concentration of A, which is 0.18 plus 2x squared. Now, in this example, I don't have a nice squared term in both the numerator and denominator of my expression. And to make an expression where I can solve for x is going to be a little more complicated. And oftentimes in these problems we end up with a quadratic, and we need to use the quadratic equation. In this course, I'm not going to make you memorize this quadratic equation. If you have this kind of a problem and you're asked to solve it on a test or quiz, it will be given to you. But you should be aware that not all problems are so simply solved as the ones in this presentation. Okay, so that's it for equilibrium concentrations. But remember, when you're approaching problems of this type, you want to go through this equilibrium table and this kind of logical process of solving.